Thank you. I guess I'll be faster than expected. They've already presented all the background needed in the previous couple of presentations, so I'll have a much easier work. I am gonna focus on end-to-end transport services on MobilityFirst, but I'll try to give a slightly different approach to the problem than the usual MobilityFirst presentation. So, end-to-end transport protocols, as we all know, have always been focused on providing different type of services in the IP context, which means that all the communications were based on end-to-end, on machine-to-machine in particular communications. So I just listed some of the most common transport protocols, but there is an important question that we ask ourselves. How do we change what a transport protocol is, what type of services and requirements we expect from it when we transition to an information-centric network? And Mohammed actually already talked about it, so I won't go through the details of what an information-centric network is, but I'll mostly focus on the fact that as we transition from host-centric communications to content-centric, information-centric communications, we transition to a different set of requirements, which include the ability of transfer content, possibly from multiple locations. So we have to consider as a norm multi-point communications, and we need to provide communication in an environment where the end hosts are only relying on the name of the objects that are referenced to and not on their location. So I just provided a couple of examples of what are some of the most common information-centric networks, which are content-centric networking and DONA, which is a paper from about 10 years ago now. And maybe now you're asking, why am I talking about information-centric network in a MobilityFirst talk? Well, simply because it turns out that MobilityFirst actually provides all the abstractions that are required by an information-centric network, which is, as I was saying, name-based services, the possibility of address contents, and not only contents, also services and devices and other more abstract network objects like context. And finally, native support for multi-point addressability, which are all the components that we normally find in information-centric network. And moreover, it turns out that for as much as information-centric networks have been around for some time now, not much work has been done in trying to actually formulate the set of requirements that are needed from the end hosts. We always focus a lot on what's needed by the network to provide the support for the communications, but we kind of forgot what's needed by the end host, which is kind of difficult to think about, because when first IP and TCP were presented, actually the transport and the network part was presented at once altogether. So I actually removed a few slides about MobilityFirst. We already talked a lot about today, so I'll just remember you a couple of concepts, which are that we have a complete separation between names and their locations. We have this concept of globally unique identifiers that provide names to devices, and not only devices, but also contents. And we have a name resolution service that provide the mappings between the names and their locations. Finally, we have a set of architectural design choices that we have to take into account in defining the end-to-end transport protocols, which are most importantly a hop-by-hop transport, or better, transfer of large chunks in a reliable fashion. And moving forward, we also have, from looking at the top-down perspective, we want to provide, we define a new network API, MobilityFirst, which actually allows to do some more advanced things, such as retrieving contents, directly address services and request services from them, or provide different type of communications and support for multi-homing and other aspects like that. And we all it's easy to say that we want to do this from the application layer, but at the same time we need to provide support to this type of communications. So we try to summarize the set of requirements that we will then want to fulfill with our design. And I won't go through them in detail because I pretty much mentioned them already, but as you can see, we want to provide obviously support for network heterogeneity and mobility, which is, well, as MobilityFirst suggests, one of the main requirements. We want to provide support for content retrieval and multi-point communications. And we want to provide also support for additional services such as aggregation of multi-source information, like sensor information that gets gathered inside a in-network service. And finally, we want to provide a mechanism for congestion control in an environment where we have this hop-by-hop reliable transfer. So this is the general picture of our design, how we kind of envisioned it. And starting from the upper part of the slide, we see that we are not actually only focusing on the end hosts that are part of the communications, but we actually want to be able to communicate with network devices, network objects, which we call proxy transport proxies, which are adding additional features such as notifications of temporary storage, which is supposed to provide support for mobility and temporary disconnections. And moreover, we want to limit the amount of feedback and control messages that happens between the end hosts, because we already have a lot of reliable services provided by the hop-by-hop transfers. So we try to limit the end-to-end recovery only to major failures when the chunks get completely lost, and to do so, I'll show you how we actually perform that. And finally, in order to provide support for the multi-point addressability, we exploit the presence of the name resolution network to provide a somewhat hybrid approach to the problem, where we use multicast addressability to send data in a multicast fashion, and then we use unicast channels to recovery from losses. And I forgot to mention that again, as the network congestion is actually, the problem of the network congestion is actually solved on a hop-by-hop manner, we only need to provide support for congestion at the end host, which corresponds to basically scale down the pace at which chunks are transmitted in the case of a lack of resources at the hosts. So moving into the details, I'll try to show you a few use cases that will give you more details about the design and some of the advantages. But first, I wanted to start from looking at the general view of how TCP will normally work. And probably you all know, but I'll go through it quickly. We have a three-way handshake connection. TCP is a stateful protocol. We need to exchange first the status between the host, and then we can proceed with the communications. And error recovery is TCP mostly uses an error recovery based on the fact that if a packet is lost in the network, is mostly due to the congestion. So it tries to estimate the end-to-end round trip time to kind of understand when a loss happens. And this is particularly problematic with the heterogeneous environment that I was mentioning before, because if we have different type of networks along the path from the source to the destination, evaluating a round trip time can be very difficult. So moving into our design, we actually look at having the hop-by-hop recovery, which actually helps us to better support the heterogeneity. So as you can see from from some of the from the results on the right, we're actually able to better provide to support constant throughput, even though we introduce losses into the final wireless connection. We provide the failure recovery on an end-to-end fashion, so a complete break of one of the routing fabric inside the network can be recovered by the endos without need of re-establishing the connection that was originally set up as done in TCP. And this is done through an hacking mechanism where the endos basically estimate what's the expected time for the receival of the complete file or the complete message that has been sent, and send feedback back only when this timeout triggers. Finally, I already mentioned the congestion control mechanism, so that the receiving part sends feedback to the other host in order to slow down the connection in case the resources on the end machine are running low. I forgot to mention that these results are actually, all the results that I'll show now are actually based on our prototype that we are implementing, and it's mostly complete, and are taken from actual machines running on orbit. So it's not simulation based or emulation based. On a similar take, the previous slide was mostly focusing on of transfer of large files. If we look at transfer of smaller files, which is usually the case for the most common scenario in the data transfer in the network today, which is basically web browsing and HTTP content in general, we can see that by the introduction of this hop-by-hop reliability and retransmission of caused by the losses on a local scale instead of on an end-to-end basis, we can in a much quicker way recover from errors. And the graphs on the right actually show that when there are losses events, we can recover much faster, and mobility and our implementation can recover from them very, very quickly. As I was mentioning before, we plan to support Multicast and Anycast communications. In particular, here I wanted to showcase how error recovery is handled on an end-to-end base. As I was mentioning, we use the Multicast delivery system in order to transmit data from the source. All the destinations will receive the data, and if there's need for recovery of information, this will be performed on a unicast channel. And this is easily accomplished using the concept of names, because we can have a multicast name which provides resolution to multiple devices, and this is the general multicast concept used for delivery. But then these unique names of the devices can be used to actually provide the error recovery. This obviously can be applied only on a smaller case, because otherwise this kind of blow up if we apply this type of concept on a larger scale. So in which case we are planning, although we haven't completely designed the scenario, to provide network aggregation of acknowledgements and retransmission on a local scale. And one question that is usually asked if when one is using hop-by-hop reliability of large chunks is how we can actually support real-time services or real-time communications. Well, this is actually in our case performed on the assumption that we have support from the network to request to disable the reliable part of the hop-by-hop. And at the transport layer, we only need to provide information about the fact that we don't need to trigger the reliability mechanisms. So, to conclude, we define the set of requirements that are needed by require from an end-to-end transport that performs on top of an information-centric network. We designed a set of solutions that should provide support for these requirements, and we are working, and we have mostly completed a prototype that will be used for exploring a set of use cases that should support our design, the qualities of our design. And this is pretty much our future work. So if you have any questions, as I said, I was pretty fast because a lot of the introduction has been done by my colleagues.